So chapter 6 is the second law of thermodynamics. So what is the second law? What's the difference between the first law and second law? So let's say this. Processes proceed in a certain direction and not in the reverse direction. So the first law places no restriction on the direction of process, but satisfying first law does not guarantee that the process can actually occur. So you can see this very well-known, easy to know example, a hot coffee sitting on a desk, and we know this coffee is getting colder and colder over time, right? Because the thermal energy or the heat is losing from this hot coffee to the environment. Okay, so this process happens in nature. Okay, however, okay, so we know this heat losing process satisfies the conservation of energy. However, if you have a heat coming from the environment to the hot coffee, then this hot coffee will be getting hotter and hotter. But this doesn't happen because of what? Because, well, this heat addition process still satisfies the conservation of energy. Okay, right? So we have Q in coming in, then internal energy of the coffee increases, satisfies the first law. But it doesn't happen, and it will never happen because this process, this heat addition process violates the second law of thermodynamics. So the second law of thermodynamics is like it's like what? It's like to define the direction of the process. Okay, so actual process, or let's just read this. So a process cannot occur unless it satisfies both the first law and the second law of thermodynamics. So a real process must satisfy both thermodynamics laws. Okay. So now later we will talk about what, how do we define or how do we state the second law of thermodynamics. But in a short way to say that is, okay, the second law of thermodynamics defines the direction of the process. Okay. Okay. Let's see this. Second law of thermodynamics. Identify the direction of the processes. Okay. Assert that energy has quality and quantity. So in first law, we talk about quantity a lot. It's conservation of energy. So the quantity is conserved. But the second law, in second law, we will talk about quality a lot, especially in chapter 7, which is entropy. Okay. So spoiler, entropy is it's like the representation of the quality of energy. Okay. All right. Third one, the second law provides necessary means to determine the quality and the degree of degradation of energy during a process. And it also determines theoretical limits for the performance of commonly used engineering systems. So just for example, we know that a car engine, the thermal efficiency of a car engine is usually around 20%, sometimes even lower, depending on the types of the engine. But 20% sounds like super low. However, there's a theoretical limit for large car engine, which could be maybe 60% or 70%. It's a theoretical maximum. Okay, so even though we know like well, ordinary people who don't learn thermodynamics before, they would think like 20% efficiency is super low. But what they don't know is there's a theoretical maximum. Could be just 60%. Okay. So in second law or in this chapter, we will talk about this. We will talk about this. What is the theoretical limits for the performance of these engineering devices? Okay. Right. So the second law is also used to predict the degree of compression of chemical reactions. We won't talk this too much. Okay. So we will focus on the quality. We will focus on these four. Okay. Direction of the process. This is actually based on the quality. Okay. I mean, the direction of the process. We will use the quality, or we will use the entropy increase or decrease to determine, to identify the direction of the processes. Okay. All right. So before that, before really getting into the quality matters, okay, I want to introduce an idea, thermal energy reservoirs. So reservoirs, what is reservoirs? Reservoir means there's a big something, right? Like a big lake, ocean, river, or atmosphere. They can be reservoirs. So reservoir is like something very big. Okay. So this something means it can, well, when we talk about something, usually that means, okay, so this something has mass, right? We know mass carries energy, right? E equals mc squared. Okay. So thermal energy reservoir means this reservoir contains a lot of energy. So from this equation, we know if energy is super big, let's say, just say if energy is infinity, then the mass is infinity. Okay. All right. So, but well, we know in reality, there's nothing that has an infinite mass, right? So this is just like a hypothetical body with a relatively large thermal energy capacity, which is mass times the specific heat. So relatively large. Okay, so this idea is very important. It's as long as it's relatively large, it can be a thermal reservoir. So for example, like the atmosphere in my office can be a thermal reservoir with respect to myself. Okay, or with respect to this hot coffee. I just made this like 10 minutes ago. Okay. So here is the idea. Okay, so I have this hot coffee. It's pretty hot. I made this like 10 minutes ago. Okay, so now it's getting warmer and warmer. But we know this coffee is getting colder. It's getting warmer. No, I should say it's getting colder because the heat is lost to the environment, to my office, to the air in my office. However, do I feel the temperature of this room hotter and hotter? No, absolutely no, right? But we know there's some energy, thermal energy coming out of this hot coffee, but I don't feel anything. Okay. So theoretically, reservoir means it can supply or absorb finite amount of heat without undergoing any temperature change. Okay. So if the air in my room, in my office is reservoir, then as long as it's a reservoir, that means the temperature of the reservoir doesn't change, no matter what. Okay. So temperature of a reservoir doesn't change, no matter what. Okay. Well, you may argue that I just can't feel it. Okay. There's a change, but not a lot. So we cannot say that the temperature of a reservoir doesn't change. It changed, but just a little bit. Okay. But here the idea is, well, reservoir, we don't have an actual reservoir, right? Because the reservoir is, well, if you have a reservoir, then the temperature doesn't change, of course. But in reality, we don't have an actual reservoir. So reservoir's temperature changes. Okay. Well, this is controversial. Okay, but like here it says, it's a hypothetical body. So it's not real. It's not real. We just assume this finite, this super small temperature change is negligible. Okay, that is the idea. Like this. Okay. A living room, the air, the atmosphere in this living room is the reservoir with respect to teapot, like T-top, and maybe lamp, maybe something else. Okay. Okay. So the body does not actually have to be super big to be considered a reservoir. So as long as it's relatively big, that's enough. Okay. So any physical body whose thermal energy capacity is large, relative to the amount of energy it supplies or absorbs, can be a thermal reservoir. Okay, so here we know that a thermal reservoir does not, it's not necessary to be a super big stuff, ocean, river, mountain. I'm not sure if mountain, yeah, I believe mountain could be a reservoir with respect to, I don't know, camping fire, things like this. Okay, as long as it's relatively large, okay, that's enough. Okay, then we have two types of reservoir. One is sink, one is source and sink. So source is used to supply energy in the form of heat. Then sink is used to absorb energy in the form of heat. Okay, so sometimes source can be like, usually we call a source high temperature reservoir. High temperature reservoir. Sink is low temperature reservoir. Okay, this is source and sink. Source is to supply, is to provide energy. Sink is to absorb energy. Okay, so one is high temperature, the other one is low temperature. Okay. Thermal pollution. Well, irresponsible management of waste energy can significantly increase the temperature of portions of the environment. Okay. like this open fire. This is super common in Taiwan. Okay, when you want to cook, Taiwanese would use open fire to cook. Okay, like this. So you can imagine there will be a lot of heat loss. A lot of heat loss means a lot of energy loss. Okay, when using open fire like this. Okay, so in North America, when I was a graduate student over there, we use this electric stove. Okay, it's more energy efficient, but someone says the taste of the food cooked by open fire and electric stove like this will be different. Okay, but I don't this. I'm not like a picky guy in eating, tasting this stuff, so it doesn't matter to me. So I felt good. I felt food is good. It's fine for me if cooked by the electrical stove like this. Okay, but this one, like open fire, I think there's a lot of development focusing on how to minimize the heat loss, the energy loss when using open fire. Okay. And this picture, this is a nuclear power plant in Taiwan, in Pingdong, in Kending, I believe. Okay. So, well, we know that the temperature around the outlet of this kind of nuclear power plant is a little bit higher. Okay, so a couple of years ago, there's a issue that the fish around the outlet of a nuclear power plant is like so weird. So, you know, it's the baby fish is the baby fish doesn't look like a fish. Things like this. Okay, so you can Google this news. I think it's just maybe 10 or 20 years ago, not so long. Okay. All right, heat engines. Okay, so we know that in thermodynamics, in mechanical engineering, the purpose of learning thermodynamics is we want to build a heat engine that has super good efficiency, that can do a lot of work. Okay, so heat engine, I would say this guy is the most important application of thermodynamics in our field. I mean, in mechanical engineering. Okay. So look at this. Heat engines are used to convert heat to work. So it's a work producing devices. It's similar to turbine. We know turbine is used to produce work. Heat engine is also used to produce work. However, turbine is a single steady flow device. Okay, but heat engine, a heat engine contains or consists of several devices, several steady flow devices, and turbine is one of them. Okay. So we will talk about this, but here I'm just telling you that a heat engine consists of, I think it's minimum 4 steady flow devices. And these devices, the combination of these devices is used to produce so-called net workout. And we will see this later. Okay. All right. So let's see this. Heat engine receives heat from a high temperature source. So this is the source, and the source is usually a high temperature. Okay. For example, the source could be solar energy, furnace, nuclear reactor, things like this, okay? And heat engine converts part of this heat to work, so usually in the form of rotating shaft. So this work is usually like shift work. Just like a car engine. So the work output of a car engine is actually shift work. Then the shift connects to tire so that you feel like, okay, so when you are in the car, you could feel the acceleration, you could feel like you are moving. You might think, okay, so now your kinetic energy is higher and higher and higher because the velocity is increasing. But actually, the engine delivers work just to the shaft. Then, so it delivers shaft work. Then the shaft connects to tire, and the tire rotates, and the tire, the whole car, the chassis, you're sitting in the car, then you're moving forward because of the this work. Okay. All right. Then, well, we know that you probably don't know why, but at least we know that an engine, the efficiency of an engine cannot be 100%. So based on the conservation of energy, we know there are some energy that has to be rejected to the environment. Okay. So here it says the heat engine rejects the remaining waste heat to a low temperature sink. Okay. So high temperature source or low temperature sink, they are reservoirs. Okay. The temperature of the reservoir doesn't change. Okay. That's the key. Okay. And heat engine operates on a cycle. So heat engines are cyclic devices. Okay. So that means the engine is like keeping moving. Okay, it delivers the work output after one cycle of the process. Okay. Okay. So the working fluid of a heat engine. So the fluid used in the cyclic devices in which heat can transfer to or from, that is the working fluid. So it could be water, could be refrigerant, could be anything else. Okay, as long as the mass capacity is enough, is large enough. It's large enough. Okay, so working fluid. Okay. Internal combustion engine, like gas turbines, car engines. So internal combustion engines means the combustion happens inside the engine. So we know car engine is an internal combustion engine. So you can see the this is the schematic of an car. I think this is a four-stroke car engine. Okay, four-stroke cycle. So the combustion happens inside the pistons in the device. Okay. So this is internal combustion engine. Okay. Well, but internal combustion engine operates in a mechanical cycle, but not in a thermodynamic cycle. So this cycle, we know the crankshaft rotates. It always rotates like this, right? So, but internal combustion engine is not in a thermodynamic cycle because we know the fuel comes into this engine mixed with the air, then combustion happens, the exhaust air expels out, right? So this fuel or this air fuel mixture does not, it's not recycled again, right? Because after burning, after combustion, this exhaust gas is not going back to, it's not going back as a new air-fuel mixture, then into the system, then make the combustion happen again, right? So it's not in a thermodynamic cycle because every cycle, the air-fuel mixture is like renewed. Okay, so these exhaust gases, they are not going back to the system anymore. Okay. External combustion engine is like power plant. Usually, most of the power plants are external combustion engines. So the difference between internal combustion engine and external combustion engine is the place that where the combustion happens. Okay, so we know internal combustion engine means the combustion happens inside the engine. External combustion engines, literally, combustion happens outside of the engine, external to the engines. Okay, so combustion takes its place outside of the engine. Okay, so thermal energy released during this process is transferred to steam as heat. So each single component. So we will be focusing on external combustion engine in this chapter. Okay. So, like I said, a very typical heat engine consists at least of 4 steady flow devices: pump, boiler, turbine, and condenser. Please keep this schematic in mind. That means you need to memorize the schematic of this very typical heat engine. Okay. Pump, boiler, turbine, condenser. Okay. So the thermal energy released during this process is transferred to the steam as a heat. So boiler is used to receive heat from the combustion, maybe from a furnace, from a nuclear reactor, things like this. So this is essentially an energy source. This is source, which is a high temperature reservoir. High temperature reservoir. Okay. So boiler gets some energy from high temperature reservoir. Then the working fluid in this pipeline, maybe the water, if we are talking about steam power plant, then the working fluid is water in this pipeline. Okay. So you can imagine the hot water. This is cold water. This is hot water, right? Then the turbine extracts energy from the fluid. So hot water after that maybe becomes cold water again, or maybe just warm water. Okay. Then turbine produces work. Okay. Then this warm water goes to condenser. Then condenser is used to reject the waste heat to an energy sink. So this is a low temperature reservoir. Okay. So warm water maybe become like cold water, something like this. Okay. Then pump increases the pressure of the working fluid, right? So this is cold water, high pressure, right? Because the water is being compressed by the pump. So we know the pump requires work input. This is what a pump does, right? It transfers the energy to the fluid by rising its pressure, right? Okay. So this is a high pressure. This is still high pressure. And turbine after turbine, this becomes low pressure, right? Okay. All right. So this schematic, this diagram is super important. Okay, so you need to keep this in mind. Okay, and we know this is the reason why we learn chapter 4 and chapter 5, which is steady flow devices, right? Energy analysis of the steady flow devices. So you need to know how to analyze pump. You need to know how to analyze turbine, things like this. The boiler and condenser, they can be like just a duct. Okay, we know the duct, right? The duct is just a pipe. Then you can give the energy to the duct in the form of like electrical energy, or if you want, you could just say there's a Q in or there's a Q out, right? Things like this. So the boiler and condenser, they're just a very simple pipe. And we know we could treat pipe as a steady flow device in this class. Okay. So every single component should be treated as an open system, and is steady open system. Okay. This is steady. Okay. The entire engine can be analyzed as a closed system. So by definition, we can do that, right? Because by definition, the closed system means there's no mass coming in or out of the system. So every single device in this heat engine is a steady flow device, and choosing the entire engine as one single system, then this system, this heat engine is a closed system. Okay, so of course you need to know the definition of closed system and open system, so you can conclude like this. Okay. All right. So for a closed system undergoing a cycle, the change in internal energy is zero, right? Because from the energy balance equation, we know E in minus E out is delta E system. This is U2 minus U1, okay? If the process is cycle, that means the initial state, I would say the final state, is the same as initial state. So that means U2 equals U1. Okay. So when U2 equals U1, then we know this is zero. This is what the statement says here. For a closed system undergoing a cycle, the change in internal energy is zero. Okay. So E in minus E out is zero. Okay. So E in minus E out is zero. Okay. So if we break down E in and E out, these two terms, for a closed system, energy can be transferred by heat and work, right? So the diagram here shows us that, okay, so pump has a work input, boiler has, sorry, pump has work input, boiler has heat input, turbine has a work output, condenser has a heat output. Okay, so together the summation of these four energy transfer mechanisms is, or just for energy transfers, the summation of these four should be 0, right? So Q in plus work in, right? These two are energy transfers to the system. Work out, Q out, minus work out, minus Q out. So these two are energy transfers to the environment, from the system to the environment, right? So the summation of these four guys is 0. Okay, so the we can conclude this. Just to do rearrangement, work out minus work in is Q in minus Q out. Okay, but here we define work out minus work in is net work out. Net work out. Okay, so we will be using this idea a lot. Net work out or net work in. Okay, so net means there's a difference. Okay. Net out means something out minus the same thing in. Okay. Net in is something in minus the same thing out. Okay. So work net out is work out minus work in. Q net in, this is Q in minus Q out. The idea is the same. Okay, as long as you know this. Net out is out minus in. Net in is in minus out. Okay. All right. So, but usually we don't say this like Q net in. But saying Q net in, it's nothing wrong. But we just don't do that. Okay. But we do this a lot. We do net out a lot because this is what we care the most. We want to know how much work this heat engine can produce. So this guy is what we care about the most. Okay, so we have this name. Okay, but because we know the turbine produces work, however, pump consumes work. Okay, so combine the effects from these two devices. This is why we care about this net out. Okay, because we have work out from the turbine. However, pump consumes some power, consumes some work. So the combination of these two works is what we care about. Okay, so net work out. All right. So going back here. So we know that, okay, so we want to like maximize the network output of this heat engine. The heat engine is used to produce power, so of course we want it to produce as much power as possible. Okay, so in this case, we can see that, okay, one way to do it is, okay, we can increase Q in, of course, right? Net work out is proportional to Q in. As long as we have very large Q in, then we have very large Q out. I'm sorry, we have very large work out. Okay. Another way to do it is, okay, so this Q out is, it's part of the process, right? The condenser dumps, or we can say the heat engine dumps the waste energy to the environment, to the energy sink. We have Q out. So can we minimize Q out, or can we make this zero? If we don't have this condenser, we don't need to dump the so-called waste energy to the energy sink. Then net work output is maximum. Okay, it's the same as Q in. That's wonderful. Okay. So Q out represents the magnitude of energy wasted in order to complete the cycle. However, unfortunately, Q out is never zero. Okay, Q out is never zero. We will tell you why later. Okay. The net work output of a heat engine is always less than the amount of the heat input. Okay. So we know the net work output is Q in minus Q out. Okay. If you believe this, Q out is never zero, then this statement is correct, right? Q out is never zero, it's always positive. So the net work output is always less than the amount of the heat input. Okay. So in other words, only a fraction of the heat transferred to the heat engine is converted to the work, of course, okay, because Q out is never zero. Okay, so now we know Q output cannot be saved. No, Q out cannot be zero, but we can try to like minimize Q out to save energy or to increase the thermal efficiency. Okay. So the fraction of the heat input converted to net work output is a measure of a heat engine, which is the thermal efficiency. So don't forget, in chapter 1, we define, this is how we define efficiency, right? Which is desired output over required input. Keep this in mind because we will be using this for different types of devices. And even though for the same device, if the purpose is different, so the purpose of a device is the desired output. So for example, like for the refrigerator or heater, heat pump, they are actually the same device. But because the heat pump, the purpose of a heat pump is to heat up a space, and refrigerator, the purpose of a refrigerator is to cool a space. So these two devices sounds like, it sounds like, okay, so they are two different devices, but actually they are the same device. They are the same device, but the purpose is different. So how do I say this? Let's say this. Okay, if this is a heat pump, it's also a refrigerator. Okay, then the heat pump is to heat up a space. Okay, so this is the room, a living room, an office, whatever. So the heat pump is, okay, I want to add the energy to this space, right? When you add energy to a space, the temperature of that space increases, right? But for this space, this should be the space in a refrigerator, right? So it will be a cool space, a cold space, okay? So even though heat pump and refrigerator, they are essentially the same device, but because the purpose is different, so even though they are the same device, the thermal efficiency will be different, okay? We will see this later, okay? So this is what you need to keep in mind. The definition of the thermal efficiency, which is desired output over required input. Okay. All right. Just for example, okay. Yeah. Another thing I want to mention is the schematic of heat engine, refrigerator, and heat pump, like I just drew. Usually, this is how we draw this device. Okay, I would say this devices. So the device is usually made in this circle. So it could be heat engine, could be heat pump, and could be refrigerator. Okay, then up here, this is usually like high temperature reservoir or source. High temperature reservoir. Okay, whatever, whichever you want. Okay, down here, this is energy sink or low temperature reservoir. Okay, so this arrow represents the energy transfer or heat transfer. So this could be Q, I want to say Q in or Q out. Here, this could be Q in or Q out, depending on the depending on the device. Okay, and the device either has like work input or work output. So this could be network input or output. Okay, so this is how we make a schematic of the device, the heat engine, heat pump, or refrigerator. Okay. All right. Like for example, this is apparently this is a heat engine, right? Because there's a work output. There's a work output. So this has to be a heat engine. Okay. So the net work output of the engine one is 20 kJ. Okay. Then the waste heat is 80 kJ. The heat input is 100. So by definition, the thermal efficiency is desired output. This is the network output is the desired output of a heat engine. So desired output of this heat engine is 20. Okay. Required input, this 100 kJ, this is the required input of this heat engine. So the thermal efficiency is 20%. Okay. Well, if the network output is 30%, heat input is still the same, 100 kJ, then for heat engine two, thermal efficiency is 30%. Okay. So in this case, what I want to tell you is, okay, so this, the waste heat here is not so important. Well, I cannot say this, but the idea, see, the desired output, required input, there's no like waste heat in this case, right? But however, if you know the required input is the desired output plus waste heat, right? This is desired output. Okay, so waste heat, like it's hidden in the required input if you want. Okay. Okay. So yeah, here is the math. Okay. If this is a heat engine, then we have a net out. Okay. So you probably know, okay, so this is pump, this is turbine. So turbine pump has work in, turbine has work out. But together, because the one is work in, the other one is work out. And this heat engine is used to produce power output. So what we care about is, yes, it's a combination of work in and work out, which is net work out. So usually in the schematic, we would have just like this, the one single network output. Okay. And okay, so we have a QH, which is actually Q in, heat input to this heat engine. Okay. QL is Q out, the waste heat dumped out of the heat engine. Okay. So by definition, we know the thermal efficiency is desired output, which is network output, over required input. I was just right here. So this is the desired output. Then this is required input. Okay. All right. And okay, from the energy balance, we know what? We know QH is network output plus Q out, right? One coming into a system, two go out of the system, and the summation should be the same as the one that comes into the system. Okay, so network out is QH minus QL, right? Network out is QH minus QL. Q out here, this is QL. Okay. All right. So simple math, right? 1 minus QL over QH. Okay. All right. So now question is, can we save Q out? Yes, we can save Q out, but we cannot make Q out 0. Okay. So every heat engine must waste some energy by transferring it to low temperature reservoir in order to complete a cycle. Okay. So here another important concept is we have to transfer it to a low temperature reservoir. Okay, so here is the idea. Okay, so let's look at this. A piston cylinder device, and we have 2 sets of stop. This is one set. This is another. Okay, so the piston can move in between. Okay, so now if the piston connects to a load, like a shaft or whatever the load is, okay, and then we bring this piston cylinder device into contact with a reservoir, high temperature reservoir, let's say 100 degrees. Okay, so we have a heat input 100 kg to make the piston moves up to this position, and we want to increase the temperature of the gas to 90 degrees. So from 30 degrees to 90 degrees. Okay. And you know that. Okay. So the piston, we have a load sitting on the piston, and this piston is moving up because it receives this amount of energy. So piston and load move up to this upper stop. Okay. So let's just say, okay, if we don't have this load, then the heat input to the system to make the piston moves to the upper stop while the gas temperature increases to 90 degrees. If we don't have this load, then the amount of heat supplied to this system might be just like 85 kg. Okay, so in between the difference, 15 kg, is used to what? It's used to do the potential energy, right? For this load. Okay. If we have load, then the energy required to do this movement is 100 kg. If we don't have this load, then the amount of energy supplied to for this movement is just 15 kg. And we know this 15 kg, we need this additional 15 kg because the load, we convert some energy to the potential energy for this load. Okay. So, yeah. So this 15 kg is transformed to potential energy. Okay. All right. So now let's remove the load, and we want to see if lowering the gas temperature to 30 degrees, can we get this like 85 kg back? If you bring this piston cylinder device into contact with this reservoir, right? We receive 100 kg from the reservoir. We want to get it back. If we can have like 100 kg back to this reservoir, then that's 100% efficiency, right? But we are unable to do that because of what? Because this is 90 degrees. This is 100 degrees. So in nature, the process cannot happen. This heat transfer process cannot happen, right? Because the heat transfer is always from high temperature media to the low temperature media, right? So now gas temperature is just 90 degrees, but the reservoir's temperature is 100 degrees. So this heat transfer is not possible. Okay, so instead, we need to bring this piston cylinder device into in contact with a low temperature reservoir, let's say 20 degrees. Okay, so that this heat transfer process can like actually happen. Okay, so we can just dump 85 kg energy to this low temperature reservoir to bring the gas temperature back to 30 degrees. Okay. So the waste heat is required to complete a cycle. So even under an ideal condition, like, okay, so we don't consider the weight of the piston, we don't consider the friction between the piston and the cylinder, it's ideal. Okay, so even under a very, very ideal condition, there must be some waste heat. And this waste heat has to be transferred to a low temperature reservoir. So this example implies two conclusions. One, there must be some waste heat. So in other words, Q out cannot be zero, right? The other implication is that to complete the cycle, to complete this thermodynamic cycle, this system has to transfer the energy with two reservoirs. Okay. One is high temperature reservoir, the other one is low temperature reservoir. It has to like have two heat transfer processes associated with two reservoirs. One is high temperature reservoir, which is energy source. The other one is low temperature reservoir, which is energy sink. Okay, so two conclusions from this example. Q out is never be zero, and it's always positive. There must be some Q out. The other one is this cyclic device has to have the heat transfer processes with two reservoirs, high temperature reservoir, the other one is low temperature reservoir. Okay, that is the idea. This example, heat is transferred to a heat engine from a furnace at a rate of 80 megawatts. If the rate of waste heat rejection to a nearby river is 50 megawatt, determine the network output and thermal efficiency for this heat engine. Okay, so from the first law, which is the conservation of energy, we know QH dot should be the summation of the network output and heat rejection, right? This is Q in, one Q in, and we have two outs, one in, two outs, and they have to be the same. Okay, so we can get network out easily, which is 80 by minus 50. So we have 30 megawatts network output. Okay. Then thermal efficiency is desired output over required input. Okay. So desired output is just the network out. Required input, we have only one input. That is the thermal efficiency. Okay. Simple, straightforward. Next one, a car engine with a power output of 65 horsepower has a thermal efficiency of 24%. Determine the fuel consumption rate of this car if the fuel has a heating value 19,000 BTU per LBM. Okay. Well, you need to know the how to convert horsepower into BTU, right? Okay. So how do we do this? I don't know 65 horsepower equals to what kind of BTU, how much of the BTU. But here, the idea is, okay, so we know the thermal efficiency. This is network output over QH dot, this is 25%, so 0.24. Okay, and we know this is 65 horsepower. So we know QH dot is 65 over 0.24, this horsepower, right? Is to 70.83 horsepower. Okay. All right. So this QH is the fuel consumption. Okay. So I think all you need to do is to convert horsepower into BTU. Okay. Then divide by this 19,000 BTU LBM. So you can know how much LBM the fuel has to be consumed. Okay. All right. Next one is Kelvin-Planck's statement. Well, the entire second law of thermodynamics can be like constituted by two statements. One is Kelvin-Planck statement. The other one is Clausius statement. So these two statements are like the foundation of the second law of thermodynamics. So very, very important, and you need to like really understand what these two statements are. Okay, so look at this. It's impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. Okay, it must have both high and low temperature reservoirs. So, like I just mentioned, a cyclic device has to like interact with two reservoirs. One is high temperature reservoir, the other one is low temperature reservoir. So this device receives heat from the high temperature reservoir and rejects heat to a low temperature reservoir. Okay, so the number of reservoir a cyclic device has to interact with is two. Okay, two reservoirs. Okay, and this is actually one of the Kelvin-Planck statements. Okay. The other one is no heat engine can have a thermal efficiency of 100%. Whatever is the idealized or the actual engines. Okay, so even for an ideal, very, very ideal heat engine, there's no friction, there's no heat loss, there's no whatever stuff. It's ideal, it's perfect. A perfect heat engine cannot have a 100% thermal efficiency. And this is a limitation, not due to other dissipative effects like friction or others. Okay. So Kelvin-Planck's statement, you need to memorize, you need to keep this in mind. Kelvin-Planck's statement states that a cyclic device has to interact with two reservoirs. And no heat engine, no cyclic device can have a 100% thermal efficiency. Okay. Very, very important. Okay. All right. Refrigerators, so heat is transferred in the direction of increasing temperature cannot occur by itself. Okay, so we know in nature, the heat, the thermal energy, the transfer of the thermal energy has to be from high temperature medium to a lower temperature medium. Okay, in nature. Okay, but can we transfer the energy from a low temperature medium to a high temperature one? Yes. This is what a refrigerator does. Okay, so yeah, it's a refrigerator, right? You know, in your refrigerator, you have a refrigerator, and you know, inside the refrigerator, the space inside a refrigerator it's colder than the ambient, right? This is actually a heat transfer process. It's like the refrigerator like sucks, absorbs the energy inside its space and dumps the energy to the ambient. So I'm not sure if you have if you're aware that the surrounding of a refrigerator is a little bit hotter than other spaces, right? So this is because this guy, a refrigerator, like absorbs the energy inside the refrigerator, and then dumps this energy to the environment. Okay. And you know that a refrigerator consumes work, consumes electrical work, right? You need to put the plug into the wall plug, so the refrigerator works. Okay? So heat is transferred in the direction of increasing temperature cannot occur by itself, but the heat transfer from a low temperature medium to a high temperature medium requires special devices, which is a refrigerator. Okay. So discharging heat to a high temperature medium is merely a necessary part of operation, not the purpose. Okay. So we know, for example, like heat engine. We have talked heat engine a while, right? This is TL, so we have Q in, we have Q out. Okay, this is a heat engine. Okay, so now we are looking at the refrigerator. So we know a refrigerator consumes work, so there's a work in, which is electrical work in. Okay. Okay. Then we need to we are transferring the energy from a low temperature medium to a high temperature one. So we want to transfer this energy from low temperature medium to high temperature one. Okay. So this is QH, this is QL. This is the schematic of a refrigerator. Okay. Okay. So let me share this. Okay. That's not good. A refrigerator requires work input and two reservoirs, right? From the Kelvin Planck statement, this cyclic device, the refrigerator, requires to interact with two reservoirs. Okay. And the purpose of a refrigerator is to transfer energy from a low temperature medium to a high temperature medium. So this is a low temperature medium, this is a high temperature medium. Okay, we have okay. Okay. So now you can see TL, this space should be the space inside the refrigerator, right? okay? Because the energy in this space is like keeping sucked out, okay? So, or being transferred to a high temperature medium, which is ambient. Okay, so that's why I just said that you can feel the surroundings, the ambience surrounding a refrigerator is usually hotter than elsewhere. Okay, this is why the reason is that a refrigerator like actually dumps some energy or transfer some energy from inside out. Okay, this is inside, this is outside. Outside refrigerator. Okay. So yeah. So this is the how a refrigerator looks like, the schematic. Okay, and we know it requires work input. Okay. All right. So but here actually this is what I want to talk about. Discharging heat to high temperature medium is merely a necessary part of the operation, not the purpose. So this is not the purpose. This is the purpose. Refrigerator, we want to cool the space inside the refrigerator. Right? This is the purpose. But QH dot here is not the purpose. But from Kelvin Planck's statement, we know this cyclic device has to interact with two reservoirs. And the heat rejection cannot be saved to zero, right? It must reject some heat. And in this case, QH dot is the heat rejection, okay, right? Because now we are talking about R. So what is being rejected? QH dot, okay. This is the heat rejection, okay. So it has to interact with two reservoirs. It has to have some heat rejection, okay. So these two conditions satisfy, okay. Okay. So this is what a real refrigerator looks like, okay. This is the real one, right? So, but I like to see this one because it looks better and simple, easy, okay. So there's an expansion valve, which is throttling valve, okay. There's an evaporator. So evaporator is used to receive heat from a reservoir, okay. Then there's a compressor. Okay, we know a compressor consumes work. So there's a work input. Okay, condenser is used to reject heat to another reservoir. Okay, so QH is the heat transfer to or from the high temperature reservoir. So in this case, such as kitchen air, which is the surroundings around this refrigerator, okay. QL is the energy transfer from a low temperature reservoir. So this H and L, this H and this L, they represent high temperature reservoir and low temperature reservoir, okay. No matter what is to or from, we always use QH in high temperature reservoir side we always use QL for low temperature reservoir side. So like, so you can see the difference between the heat engine. Heat engine, we have high temperature reservoir, low temperature reservoir. So for heat engine, the heat is received from the high temperature reservoir. The waste heat is dumped to low temperature reservoir. So, but in refrigerator, QH is to high temperature reservoir. QL is to the refrigerator. Okay, so see the direction, this direction and this direction is different, but we still use QH. So we still use QH or QL to represent the interaction between the device and the reservoir. Okay, it doesn't matter about the direction, QH or QL. Okay, so you need to specify the direction by yourself. Okay. Okay. So a vapor compression refrigeration cycle. Okay. So we have a compressor. It compresses refrigerant from low pressure vapor to high pressure temperature. Okay. See, the compressor compresses refrigerant from low temperature vapor, like in this case, 120 kilopound to 800 kilopound. So now the working fluid is refrigerant. So it goes to like, this is counterclockwise, okay. All right. Then condenser rejects heat to surroundings and cool down the refrigerant, okay. So from 60 degrees to 30 degrees. Pressure is the same. Pressure is the same. See. Then expansion valve used here uses the throttling effect to drop the temperature and pressure. Right. So you can see pressure, temperature, they both drop. Okay. And don't forget for throttling process, the characteristic is the enthalpy doesn't change. Okay, the enthalpy doesn't change. Okay. Evaporator is like to what? To receive the energy from a low temperature reservoir. Okay. So it absorbs heat and evaporates working fluid or refrigerant to vapor. Okay. So this is a cycle, a complete cycle. Okay. But here, okay, let's talk about efficiency. Remember the definition of the efficiency? We said the efficiency is desired output over desired output over required input. Okay. So for refrigerator like this, the desired output is what? This is the desired output because we want to make this space cooler and cooler, right? So QL in this case is the desired output. This is QL. What's the required input? Of course, this is the required input. Okay. So the network in is a required input. But from the energy balance, we know that these two ins, the summation of these two ins QL and net work in should be the same as the QH, right? So QL plus net work in is QH. So net work in is QH minus QL. So this is QH minus QL, okay. All right. So now question is, so we can do this. We divide QL on both sides. So this is QH over QL minus 1, right? Okay. And we know QH is larger than QL. Okay. So this should be like greater than 1, right? QH over QL is greater than 1. So there's a chance that this is larger than 1, right? If QH over QL is 1.1, then this is 0.1, 10. This is 10, right? Just for example, this is 10. So 10 is what? Times 100. So this is 1000%, right? It's larger than 1. It's larger than 1. So using this traditional, or let's say this, when we say efficiency, efficiency is defined between 0 to 100%, right? This is how we usually use efficiency, this word. Okay, it's from 0 to 1 or 0% to 100%. Okay, if we follow this is still the truth. Then we end up with like more than 100% efficiency. Okay, so in this case, we don't call this efficiency. We call this coefficient of performance, aka COP. Okay, so you will hear this if you want to buy a refrigerator. The value you need to evaluate the efficiency is not thermal efficiency anymore. Okay, it's usually denoted by COP, coefficient of performance. Okay, so yeah, this is what I just wrote. Okay, so we don't call this efficiency anymore. No, we don't use this term because efficiency implies that the maximum is 1 or 100%. So instead, we use COP. So the value of COP can be greater than 1. Okay, can be greater than 1. It depends. Okay, and R here represents refrigerator because later we will talk about the heat pump. So COP, HP. So HP here means heat pump. Okay, and these two devices are the same. Heat pump and refrigerator, they are the same device, but the purpose is different. We will talk about heat pump later. Okay. So the value of COP can be greater than 1, as you can see, because QH is larger than QL. Okay, so depending on how much larger, that decides the COP. Okay. Okay. See this. The amount of heat removed from the refrigerated space can be greater than the amount of work input. Okay. So QL and network input, they can be independent. Okay. So QL can be larger than network input. Of course, network input can be larger than QL, right? It doesn't violate the conservation of energy, right? Okay. Okay. But here, what you can see, the COP of a refrigerator decreases with decreasing refrigeration temperature. Okay. We can talk about this. How do we see this? It's actually from QH, the ratio of QH to QL. Okay. So here we are going to talk about the index we use to evaluate the efficiency for refrigerator and heat pump, just these two devices. Okay, but we don't use thermal efficiency to evaluate the performance of refrigerator or heat pump. Instead, we use coefficient of performance, COP. This is COP. Because efficiency, when we talk about efficiency, usually efficiency means something less than 100% or 1, absolute value 1, okay? But because refrigerator and heat pump, their performance or their efficiency can be greater than 1. So we don't use efficiency. We don't use thermal efficiency to evaluate their performance. So we use COP, okay? Okay, so the refrigerator and heat pump, they are the same thing. They are exactly the same thing, okay? So let's make a diagram, a schematic, okay? So this device, refrigerator or heat pump, they are like essentially used to draw energy from a low temperature medium and transfer this energy to a high temperature medium. Okay, THTL. Okay, but doing that, because this violates like the nature, right? Because in nature we know the energy transfers should like from high temperature medium to a lower temperature medium, right? This happens in nature, but transferring energy from a low temperature medium to high temperature medium, it's possible using this device, and this device comes with work. Okay. So there's a work in here. Okay. Then this is a QL, this is a QH. Okay. All right. So the performance or efficiency we use, the definition for that is the same. It's desired output over required input. Over required input. Okay. So for refrigerator, the desired output is what? A refrigerator, because a refrigerator, we wanted to cool a space like as cool as possible, right? So apparently we want to QL, we want to maximize QL so that TL, this space, can be cool, can be very, very cool, right? So for refrigerator, the desired output is QL. But for heat pump, the desired output is supposed to be QH, right? Because for heat pump, we want to like maximize the temperature in this space. Okay, so we want to maximize QH, right? In other words, we want to maximize QH. Okay, so their desired output is different, although they are the same stuff. They are exactly the same thing. Okay, desired output is different because the purpose is different. Okay, but required input is the same. Required input, whatever R or HP, they're the same, which is network input. Okay, so their COP is different. So COP refrigerator should be QL over network input. COP heat pump, it should be QH over network input. Okay. And from the energy conservation, we know QL plus network input should be the same as QH, right? From the energy balance, we know QL plus network input should be QH. Okay, so we can rewrite COP, which is QH minus QL. Network input is QH minus QL. Then up here, this is QL. And for heat pump, up here, this is QH. Then this is QH minus QL. So we can further do something which we divide by L on both sides. So this is 1, this is QH over QL minus 1. And this divided by QH, this is 1, this is 1 minus QL over QH. Okay. All right. So so you can see heat pump. Okay. So heat pump is actually COPR plus 1. Okay. COPR is QL over QH minus QL. If this guy plus 1, then that becomes QH minus QL. This is QL plus QH minus QL. That becomes QH minus QL. Then this is QH, which is COPHP. Right. Okay. So that tells us that COPHP is always greater than COPR by how much? By 1. Okay. All right. Another thing you need to notice is from the energy balance equation, this guy, we know that QH is larger than QL. It's always larger than QL because the network input is always a positive value. Okay, so QH is always greater than QL. So look at this. Look at this. QH is larger than QL. So this guy is always greater than 1. Okay. For example, if QH over QL is 1.1, then COPR could be like 10, right? If this is 1.1, this is 10. If this is 1.2, then this is like 5, right? Similarly, you can do everything like this. Okay. All right. So COPR is always, this is always greater than 1, right? Because QH is always larger than QL. Okay. Then, of course, COP-HP is always greater than 1, of course. Okay. Right. Yeah, because COPR is greater than 1. So COP-HP has to be even larger than 1 by 1. Okay. All right. Okay. So go back to the slides. We can see that the value of COPR can be greater than 1. Can be greater than 1. Okay. So let me see. QH is greater, yeah, can be greater than 1. So this is the reason that we don't use efficiency to evaluate the performance of a refrigerator, because when we talk about efficiency, we always assume like efficiency, the maximum efficiency is like 100%, okay, which is 1, right? But for refrigerator or heat pump, the efficiency can be greater than 1, okay? So we use COP instead of efficiency, okay? All right. So COP greater than 1, that implies that the amount of heat removed from the refrigerated space can be greater than the amount of the work input. Well, this makes sense, right? Because these two guys, work input and QL, work input and QL, they don't have a very strong bonding. I mean, QL, you can have network input, you can have QL like independently, as long as their summation is the same as QH, right? So network input can be greater than QL. Network input can be smaller than QL. It doesn't matter, okay? As long as their summation is the same as QH, okay? This is just a comment, okay? And for heat pump, okay, for heat pump, okay, COP-HP is always greater than 1. It's always greater than 1 because COPR is a positive quantity. Well, COPR is not necessarily always greater than 1. It can be greater than 1. Can be greater than 1. If what? If QH, like if QH is 10 times QL, then COPR is less than 1, right? But if QH is very close to QL, COPR can be greater than 1. So can be greater than 1, can be smaller than 1. It doesn't matter. Well, not doesn't matter, but I mean, can be greater than 1, can be smaller than 1, okay? But COP-HP is always greater than 1 because COPR is a positive value. Can be 0 point something or can be something greater than 1. So no matter what, plus 1, that means COP-HP is always greater than 1. Okay. So that brings an interesting point. Okay. So a heat pump functions at worst as a resistant heater, supplying as much energy to the house as it consumes. So, so you can see that a heat pump consumes power, of course, but a heat pump uses this power this work input to draw some energy, then combine these two energy together to supply to heating space, which is this space. Okay, so yeah, COP heat pump is greater than 1. So that means in terms of energy usage efficiency, if you want to heat up a space using heat pump is better when compared with the resistance heater, right? Because we know for a resistance heater, the energy transformation rate is 100%, right? All the electrical power can be transformed into a thermal energy, right? 100% for a resistance heater. But heat pump can do much more. Heat pump can use this energy to draw more energy and together to supply to this heating space. Okay, so in terms of energy efficiency, in terms of the performance, using a heat pump to heat up a space is better. Okay, so, but would you do this? That's a question, okay? Because usually the heat pump, the cost of a heat pump is usually much higher than the cost of a resistance heater. Okay, that's the point. So in reality, many like I would say not rich people like me, okay, sometimes I just use resistance heater to heat up the space, to heat up my office, my room, my whatever, okay, because I don't have money to buy a heat pump, okay. Well, honestly, now the so-called air conditioner has like cooling capacity, has heating capacity. So essentially, these two devices, they are the same. Okay. So if you are standing behind an air conditioner, you would feel like hot, right? Because air conditioner draws the energy from the room and dump this energy to the environment. So if you are standing outside or behind the air conditioner, you will feel hot. Okay. So if let's see this cartoon picture, it's interesting. So this lady is talking to her husband, like, okay, are you air conditioning the outdoors? Because his husband installed the air conditioner like not upside down, but inside out. Okay, so you can see this coil. Okay, so this is not what we usually install in air conditioner, right? So, but this husband, this guy, might have learned thermodynamics. So he is telling his wife that, no, I'm just heating the house. Well, theoretically, yes, he's right, right? And this is more energy efficient, okay? But practically, nobody would do this. Nobody would install the air conditioner like inside out, okay? So, but I mean, now a lot of air conditioner has cooling and heating functions. So there might be some like switch to switch the air condition mode to cooling or heating. Okay. And I can't remember, that's a very good example or homework. It's like a design problem, and I like that, but I couldn't find it in the textbook anymore. I'm not sure why. If there's a house, and there's a hot rock, Okay, let's say this. There's a hot rock, like 100 degrees or 500 degrees hot rock. So now question is, how do you want to use this hot rock to heat up this house with maximum temperature increase? Okay, right? If cost doesn't matter, okay, you don't need to concern about the cost issues. Okay. So, well, of course, you can just bring the rock to the house, right? Then this rock will like release some thermal energy, right? So eventually the temperature of the rock and the temperature of the room of this house will be reached thermal equilibrium, right? That works. But is this the base usage of this hot rock? Apparently no, right? Because now you have learned the heat pump. Hot rock means this is an energy source. So if you could use this energy by heat pump, so heat pump can bring additional energy, which is the electrical power consumption. So this heat pump can draw all the energy inside this hot rock together with the energy consumed to supply to this house. Okay. So using this way, we can better use the energy stored in this hot rock, okay, by a heat pump. Okay. So this is more energy efficient, but one more time, this is the case when the cost is not an issue, okay? But cost is always an issue in reality, right? Heat pump costs like a few thousand new Taiwan dollars, okay? So that's a sociology. I'm gonna say this, okay? There's a problem with this, okay? Okay, another index to evaluate the performance of a heat pump or refrigerator is EER, energy efficiency rating. So we don't use this a lot because it's just a unit conversion and it's very common in the US. Okay, so EER and COP, their relationship is just a few, looks like it's a linear equation. It's a linear relationship. So not so important, but I just wanted to let you know there's another measure to evaluate the energy efficiency. Okay, EER. Right. Look at this example. The examples in chapter 6 are like super easy, but you need to know the concept. Concept in chapter 6 is super important. Okay, look at this. The food compartment of a refrigerator is maintained at 4 degrees by removing heat from it at a rate of this much. If the required power input of the refrigerator is 2 kilowatts, determine the COP and QH dot. That's super easy, right? Because this is a COP. This is a refrigerator. So COP refrigerator is desired output over required input. So desired output of a refrigerator should be QL dot, right? Required input is the network input. That's all, right? So this is a 360 kg per minute. So over 60 to become kg per second, which is kilowatts, right? Over network input is 2. That's it. Okay. Then based on energy balance, QH dot should be the summation of QL dot plus the network input, right? Which is 2 plus 6, right? This is 8. So this is 6 over 2, which is 3. Okay, that's all. Easy. Another one is a heat pump. Okay, so a heat pump is used to meet the heating requirement of a house and maintain it at 20 degrees. On a day, the outdoor temperature drops to -2 degrees, and the house is estimated to lose heat at a rate of 80,000 kilojoules per hour. If the COP of the heat pump is 2.5, we are looking for the power consumption of the heat pump and QL dot. All right, because the house, excuse me, so the house is kept at 20 degrees. So the amount of the heat loss should be the same as the amount of the heat gain by the house. Okay, so you need to realize that this QH dot is actually 80,000 kilojoule per hour, so that the house temperature can be maintained. Okay, all right. So the COP of the heat pump is given. So COP heat pump, this should be desired output. Desired output of a heat pump is supposed to be QH. Required input is the network input. This is 2.5. COP is 2.5. Okay. And now we know QH dot is 80,000 kilojoule per hour. So we can get the network input. Okay. Then based on energy conservation, QH dot is QL dot plus network input. That's it, right? You got network input here. QH is none, so you can get QL dot. Okay. All right. Okay. So earlier we mentioned that the second law of thermodynamics can be like constructed by two statements. One, we have learned the first one, which is Kelvin-Planck statement. Then the second one is Clausius statement. Okay. So let me just remind you that the Kelvin-Planck statement, what does it say? I mean, Kelvin-Planck statement. It states that a cyclic device requires like two thermal reservoir to operate, right? So number of the reservoir has to be 2. And another point in Kelvin-Planck statement is no thermal engine, no heat engine can have 100% thermal efficiency, right? So Kelvin-Planck statement says that the number of reservoir, it should be 2. And the efficiency cannot be 100%. Okay. Just a quick review. Clausius statement, let's say this. It says it's impossible to construct a device that operates in a cycle and produces no effect other than the heat transfer from a lower temperature body to a higher temperature body. Okay. It doesn't imply that a cyclic device that transfers heat from a cold medium to a warmer one is impossible to construct. It simply states that a refrigerator cannot operate unless its compressor is driven by external power source, such as electrical motor. Okay. Then in addition to heat transfer from a cold body to a warm one, the net effect on the surroundings involves the consumption of some energy in the form of work. Okay, so this is like well, not a lousy statement, but if you want to visualize this statement, you can do this. Okay. So Clausius statement, the concept of the Clausius statement is that, okay, so we know in nature, the heat transfer has to be from high temperature body to a low temperature body, right? So, but transferring the energy from a low temperature body to a higher temperature one, it's possible by by refrigerator. Okay. So a refrigerator, the purpose of a refrigerator is to transfer the energy from low temperature body to high temperature body. We want to this energy transfer. And this energy transfer is possible by refrigerator. However, this refrigerator has to consume some power. That is the idea of the Clausius statement. Okay. So one more time. The Clausius statement is to state that transferring the energy from a low temperature medium to a high temperature medium is possible by using a refrigerator that has to consume some power. And the power is work. Okay. Okay, that's it. So in other words, that tells us that a refrigerator, you need to have these three elements: QL, QH, and network input. You need to have these three, all these three. Okay. Without any of these three energy transfer, this device, this refrigerator cannot work. Okay. That is what Clausius statement states. Okay. All right. So the second law, okay. So the second law based on experimental observations. So just like the first law, we know the energy conservation is also based on experimental observations. Okay. And Kelvin-Planck's statement and Clausius' statement, they are like negative statements. So that means they cannot be proved. They cannot be proved mathematically. Okay, so, well, because they are experimental observations. Okay, so they cannot be proved mathematically. Okay, and one more time, again, the Kelvin-Planck statement and the Clausius statement can be used as the expression of the second law of thermodynamics. So these two statements are like the fundamentals of the second law of thermodynamics. So remember, just recall that in the very beginning of this chapter, we're saying this, okay. The first law places no restriction on the direction of the process. So like hot coffee is getting colder and colder. It will not be getting hotter and hotter, right? Because even though the energy transfer to this hot coffee satisfies the first law of thermodynamics, which is conservation of energy, but this heat addition process to this hot coffee violates the second law because the direction of this heat transfer or heat addition process violates the second law of thermodynamics. Okay, so the second law of thermodynamics identifies the direction of the process, okay, unless the process satisfies the second law. Well, a real happening process has to satisfy both the first law and the second law. Okay, any process that violates either law of thermodynamics, we have two laws, right? We have four laws of thermodynamics actually. Okay, so the zeroth law is what? It's when you bring two body contact in thermal equilibrium, and this two body is in thermal equilibrium with another body, with a third body, then, well, all these three bodies are in thermal equilibrium, even though they are not in contact, right? This is the zeroth law. First law, conservation of energy. Second law is, I don't think there's a name for the second law, but the second law is used to identify the direction of the process. Okay, now you know that. Okay, and in chapter 7, we will talk about the third law. Okay, so we have four laws of thermodynamics. Okay, all right. Let's go back to Clausius statement. Okay, we finished this second law. Okay, yeah, we have finished this. Okay, now we are going to prove one thing. What is that? So any device that violates the Kelvin-Planck statement also violates the Clausius statement, and vice versa. Okay, so it looks like, okay, so the Kelvin-Planck statement talks about the number of the reservoir, right? We need to have two reservoirs, and the thermal efficiency of a heat engine cannot exceed 100%, right? Clausius statement tells us that, okay, transferring the energy from a cold medium to a high temperature medium is possible by a refrigerator that consumes power, that has to consume power. Okay, looks like these two statements, they are not related to each other, but actually they are. Okay, so now we are trying to prove that violating the Kelvin-Planck statement also violates the Clausius statement. And actually, violating the Clausius statement also violates the Kelvin-Planck statement. Okay, so let's try to prove this. Okay, okay. So now we have a heat engine. This is a heat engine, and we assume this heat engine has a thermal efficiency of 100%, right? That violates the Kelvin-Planck statement, right? And because the thermal efficiency is 100%, so this heat engine can operate with only one thermal reservoir, right? So this heat engine doesn't require the low temperature reservoir, right? Because the efficiency is 100%. So all the heat supplied by the high temperature medium, 100% converted to the network output. Okay, so you can see network out is the same as QH because thermal efficiency is 100%. So this heat engine violates the Kelvin-Planck statement. Okay, okay. So then we have another refrigerator, and this guy is normal. It's normal. It's normal, so it's doing the heat transfer from low temperature medium to high temperature medium. And this guy consumes power, and this power is from the heat engine. Okay, so the network output from the heat engine is the work input to this refrigerator. Okay, so this one works fine. Refrigerator just works fine, right? Nothing wrong. Okay, okay. Now let's do this. So now we want to choose the system, a new system. This is our new system. So this system includes heat engine and refrigerator. Okay. Right? We can do this, right? We can choose any system as we want. Okay. So now this system is transferring the energy from a low temperature medium to a high temperature medium. But okay, so we have a QH coming from the high temperature medium. But here we have energy, which is QH plus QL going to high temperature medium. So together, this heat transfer process and this heat transfer process, the combined effect is just QL going to the high temperature medium. Okay. Then down here, QL is from low temperature medium to the refrigerator, right? So nothing has been changed. It's QL, and here we don't have anything for the heat engine because this heat engine violates the Kelvin-Planck statement. It doesn't require to interact with the low temperature medium. So there's nothing here. So QL is still QL. Okay, so now question is, okay, so this is a QL, this is a QL. From energy conservation, there's no additional power input required, right? There's no work input or power input required to drive this refrigerator, right? Because if so, then that violates the first law of thermodynamics, which is the conservation of energy. Okay, so this is not required. And this system violates the Clausius statement, right? Because the Clausius statement tells us that transferring heat from low temperature medium to high temperature medium is possible by a refrigerator that has to consume some power, but this guy doesn't consume power. So this guy violates the Clausius statement. So we have proved that a device that violates the Kelvin-Planck statement also violates the Clausius statement, and vice versa. You can do exactly the same thing, just vice versa. Okay. So this is just a very simple proof. Okay. All right. Next is perpetual motion machine. So what is this? What is machine? This is a PMM. Okay. Look at this. A process cannot occur unless it satisfies both the first law and the second law of thermodynamics. We already know this. Okay. Any device that violates either law is called a perpetual motion machine. Okay. But so far, no perpetual motion machine is known to have worked. Okay. I would say, I will emphasize this so far. Okay. At this moment, at this moment, I'm talking about this so far. Okay. So that doesn't mean you won't be able to find anything that violates either law. Okay. You probably could. If one day in the future, you figure out there's a machine that violates either law, then I guarantee you could win the Nobel Prize. Okay. But well, when you deliver a lecture in Nobel Prize, you could just mention a little bit about me. Okay, so you could say that when I was in undergraduate student, when I was taking Dr. Wen's thermodynamics, he mentioned that there's no perpetual motion machine has been found by the time he gave us this big lecture, but he encouraged us to find one, and I did. So I won the Nobel Prize. Okay. Thanks, Dr. Wen, for his lecture like 20 years ago, something like this. Maybe at that time I already dead, but it's fine. I can just feel, I will feel happy for you. I will feel happy for myself as well, but it's just, well, I wanted to say joke, but this could be true, right? This could be true. Who knows? I don't know. Okay, but at least so far, there's no perpetual motion machine has been found. Okay. A device that violates the first law is PMM1. So is a perpetual motion machine of the first kind, which is PMM1. And violates the second law is PMM2. Okay, this is just a name. Okay. All right. So what is perpetual motion machine? I believe you might have seen these two examples. Okay, so this is like I don't know, a gear, and there's a rod connecting to some kind of ball or mass. Okay, and looks like this gear is gonna like rotate forever, but it won't. Okay, it won't. Another example is like this. If you have a cup of water and you make a connection, make a pipe, and like reroute to back to this water, so would this water flow continues forever? Well, you can think about this, and you can think about the reason why not. Okay, this is interesting. But the USPTO, with the United States Patents Office, they no longer consider any patent applications about perpetual motion machine anymore. More than 100 years ago, they didn't do this. Okay, and of course, they no longer accept this, even so far. Okay, so it's interesting. Frauds of PMM. Well, this is Chinese, but this is the most interesting one. So I copied this from the internet. I think it's from Wikipedia. This is the this yellow one. This is interesting. Okay. So this guy publish or describe something in this journal. Okay. I think the cleverest perpetual motion machine ever invented was one displayed in the Paris Expo in 1860s. It's super interesting. You can see this. It consisted of a large wheel with balls rolling about in its compartments. The inventor claimed that nobody would ever be able to stop the wheel because it's perpetual motion machine. So many visitors tried to stop it, but it went on turning as soon as they took their hands off it. So they like push this rotating. If this wheel is rotating in like this is clockwise, so because people wanted to like stop it, so it pushed counterclockwise. But turns out what? Turns out that okay, not a single person realized that the wheel turned on precisely because of the effort he made to stop it, right? Because of what? The backward push he gave to stop it, like enter the spring of the artificially concealed mechanisms. So it's interesting. So pushing back to this wheel is actually actually gives the energy to make this wheel turns. Okay, so this is very interesting. Of course, this is a fraud. Okay, but I think this guy has never learned thermodynamics, but this guy might be an expert in psychology. Okay, so it's just okay. Let's continue on our lecture. Reversible processes. Okay, so the following ideas are very important. I mean, rest of the chapter 6. Reversible process, irreversible process, and Carnot cycle, which is the most important stop in chapter 6, I believe. Okay, so let's look at this. Reversible process. What is this? So a reversible process that can be reversed without leaving any trace on the surroundings. Okay, that sounds well, very ambiguous, but actually, if you can see the like an example like this, let me see. Go back to this. I think this one is good. Okay. So like okay, so this is a cyclic device. There's a piston cylinder device is moving around, moving up and down. Okay. So inside this cylinder, if the process is reversible, that means okay. So any trace on the surroundings. In this case, I would say this is like the heat out, Q out, Q out. So this Q out, because the gas temperature and the reservoir's temperature, they are different. So this heat transfer process could cause some kind of trace, or another, I think is more explicit example is a cooking wheel. That picture, yeah, this guy. Okay, so this kind of open fire. Okay, the process, this heating process, this cooking process, we want to cook this broccoli and I don't know what else. Well, it's cooking anyway. So this cooking process has additional impact on the surroundings because we know there's a kind of waste heat coming out. Okay, so this effect is so-called trace on the surroundings. Okay, so if this is a reversible cooking, so we put let's say Q is 600 kg to this broccoli and everything else. Okay, and if this is a reversible process, then when we cool this cooking this stuff, then the heat release should be 600 kJ, okay, without leaving any trace. But actually, when we cook this guy, then there's a heat loss, heat waste to the surroundings. So this is a kind of so-called trace, okay. Okay. So this is what this statement says. Okay, a process that can be reversed without leaving any trace on the surroundings, precisely reversed. Okay, both the system and the surroundings return to their initial states at the end of the reverse process. Okay, because if there's a trace, if there's a trace left on the surroundings, then that means the surroundings has changed, okay, by this trace. So the surroundings cannot return to their initial state. This is the case that the process is not reversible, okay. So reversible process means both. I mean, I think this is important. Both the system and the surroundings, they have to return their initial states at the end of the reverse process. Okay. All right. It's impossible only when the net heat and net work exchange between the system and the surroundings is zero for the combined process, which is the original and reverse process, which is a cycle actually. Okay. Well, not necessary to be a real cycle, but origin process and reverse process, because they like if this is state 1, this is state 2, this is the process from state 1 to state 2, and the path is this curve. Okay. So if this process is reversible, that means when you want to go from state 2 back to state 1, you follow exactly the same path, then go back to state 1. Okay, so it's not a real cycle, right? A cycle is like this. This is a cycle. This is 1, this is 2. They are at the same point. Okay, so this is different. Okay. And this is probably the most important conclusion. Okay, I made this. How many stars? 10 stars. So that means this is so important. If the process is reversible, that means your device, if your device is experiencing a reversible process, then if your device is used to deliver work, then this device delivers the most work. Similarly, if your device is used to consume work, or your device consumes work, okay, then your device, if your device is reversible device, then this device consumes the least work. Okay, this is a very important conclusion when we learn so-called reversible process. Okay, and because of this, I mean, a device that delivers the most work or consumes the least work, this kind of device doesn't exist. Okay, that means the reversible process doesn't exist in reality. Okay, so they do not occur in nature. Reversible processes, they do not occur in nature. Okay, all right. So then why do we need to know, or why do we need to learn reversible processes? It's because we want to make a reference model when you are designing a device. So it's simply the idealizations of actual processes. Okay, so they can be viewed as a theoretical limits for the corresponding irreversible processes. Okay, so that's the purpose. We want to know the maximum or the critical, the theoretical limits, or like this. We want to know if the process, if the device we design runs in reversible processes, how much work it can deliver. Then this work is the most work this device can deliver. Or the work consumed is the least work consumed by this device. Okay, so that's the purpose. We want to know the capability, the maximum or minimum capability the device we design. If we use the reversible process, if the device runs in reversible processes. Okay. All right. Okay, so if the processes are not reversible, then they are irreversible processes. Okay, so processes that are not reversible are irreversible. Okay, so processes that cannot reverse themselves spontaneously and restore the system to its initial state. Okay, it's not reversible. Okay. The surroundings usually do some work on the system and therefore does not return to their original state. This is reality. Okay. So all the processes occurring in nature are irreversible. Okay. So again, reversible processes do not exist. Okay, do not exist. So what causes process irreversible? There are a lot of irreversibilities occur in nature. For example, like heat transfer process across a finite temperature difference. I think this is very important one. Okay. Heat transfer process across a finite temperature difference. So all the process, because of the temperature difference, well, temperature difference is a driving force for the heat transfer, right? So all the heat transfer happening in reality is irreversible. That makes sense, right? Because we know all the processes occur in nature are irreversible, and all the heat transfer across a finite temperature difference, which is the driving force for the heat transfer in nature. Then, so heat transfer across a finite temperature difference is a reversibility. Okay. So this one is important. Another one like friction, unrestrained expansion, mixing, electric resistance, inelastic deformation of solids, okay, or some other chemical reactions. So all these are irreversibilities, and there are a lot more, okay. Okay. So like, I think I want to mention this, phase compression or expansion. Remember when we talk about quasi-equilibrium? So quasi-equilibrium means the state is changing, but at any moment we want to analyze the system, we can assume the system is still. Okay, so that is the quasi-equilibrium. Okay, but phase compression or expansion, you can imagine like for compression, you can imagine that the properties at the bottom of these pistons in the device, the properties are like should be very different from the same properties but close to the piston head. Okay, this is a phase compression. But if we compress slowly, nicely, we can just assume the properties at these two different locations are the same. Okay. So phase compression, phase expansion, or this is unrestrained expansion. they are irreversibilities. Okay. All right. So the purpose of learning reversible process is we just want to know the capability, the limits of the device we design. Okay. So reversible processes can be grouped into three. One is internally reversible. Then we have externally reversible. We have another one which is externally reversible. And another one is totally reversible. Totally reversible. So this category, internal, external, or total, so they are referring the reversibilities, the location of the reversibility. Okay. Location of irreversibility. REV, I think this is REV. Okay. So internally reversible means no irreversibility occur within the system, So you can imagine if the process is externally reversible, that means there's no reversibility occur outside of the boundary of the system, or just outside of the system. Okay, then totally reversible means inside the system or outside of the system, there are no reversibilities. Okay. Okay. So it's about the location of the irreversibility. Okay. A system proceeds through a series of equilibrium states, and when the process is reversed, the system passes through exactly the same equilibrium state while returning to its initial state. Okay, so it's about the path of if this is state 1, state 2, let's say state 3. So if this is the process, state 1 to state 2, state 2 to state 3, then if the process is reversible, we go exactly the same path going back to the initial state. 3 to 2, 2 to 1. Okay. So quasi-equilibrium process is an internally reversible process because when we talk about quasi-equilibrium, the focus is what happens inside the system. Okay, we don't care what happens outside of the system. Okay, this is internally reversible. Externally reversible, so there's no irreversibility outside of the system. Okay, so the heat transfer between a reservoir and a system is an externally reversible process if the outer surface of the system is at the same temperature of the reservoir. So if we have a system, a piston in the device, if this piston is like attached with a reservoir. This is your system. If there's a heat transfer, let's say from reservoir to the system, and we know the heat transfer, the driving force of the heat transfer is temperature difference, right? In nature. But if the system's temperature and reservoir's temperature, they are the same. And under this circumstance, there's still a heat transfer from reservoir to cistern or whatever from cistern to reservoir, then this heat transfer is reversible because the temperature is the same. Okay, but this doesn't exist in nature, right? Because we know the driving force of the heat transfer is temperature difference. So if their temperature is the same, how come there's a heat transfer, right? And if this heat transfer exists, then this should be a reversible process. Okay, so this heat transfer, whatever from reservoir to cistern or cistern to reservoir, this heat transfer process has to be reversible. Okay, so recall that when we mentioned the irreversibility, heat transfer across a finite temperature difference is one of the reversibilities. Okay, so if the temperature of the cistern is the same as the temperature of the reservoir, then the heat transfer in between should be a reversible process because it doesn't exist. Okay. Total reversible, so there's no reversibility within the cistern or its surroundings. Okay, so it's about the location of the irreversibility. Okay. So no heat transfer through a finite temperature difference, no non-quasi equilibrium changes, no friction or other dissipative effects. So all the system and its surrounding, they are reversible. So it's totally reversible process. Okay. All right. So this is a totally reversible because this reservoir is at the same temperature of the system. So this heat transfer process, this Q, is reversible. It's totally reversible if there's no irreversibility inside the system. Then this heat transfer is outside of the system. So there's no irreversibility inside the system, and this heat transfer process Q is across the same, from the temperature at which is at the same temperature of the system. So this heat transfer process is also reversible. So this system is internally reversible, is externally reversible. So this system, this process is totally reversible. Okay. But if the system is internally reversible, then there's a heat transfer outside from a reservoir. But this heat transfer process happens because the temperature of the reservoir is different from the temperature of the system. So this heat transfer process is not reversible. So this system is only internally reversible. Okay, because there's a irreversibility outside of the system, which is caused by this heat transfer process. Okay. Reversible cycles. Let's see this. Recall what? Heat engines are cyclic device. Okay. The working fluid of a heat engine returns to its initial state at the end of each cycle. So work is done by the working fluid during one part of the cycle, which is a turbine, and on the other work on the working fluid during other part, which is a pump, right? So turbine does work onto the surroundings. Pump consumes work from external source, right? So work is done. So this work done, one is work out. The other one is work in, right? Turbine is work out. Pump is work in, okay? So the efficiency of a heat engine cycle greatly depends on how the individual processes that make up the cycle are executed, okay? Well, that makes sense, right? So the efficiency of a heat engine. Well, we know there are 4 components in a heat engine, right? Pump, turbine, boiler, condenser, things like this, right? So, and every device, every of these 4 devices, they can be treated as a steady flow devices, okay? So the efficiency of a heat engine greatly depends on how the individual processes that make up the cycle are executed. So we know if this is a pump, there's a turbine, a boiler, a condenser, right? So we have Q, QH, we have QL, we have work out, we have work in. And we know the efficiency is desired output, which is work out minus work in over required input, which is QH. Okay, so these 3 guys is actually, we can rewrite using QL in whatever the component. I mean, either these 3. So the efficiency of a heat engine depends on all these energy transfer, right? Whatever is work or is heat, okay? So the network, that's the cycle efficiency, can be maximized using processes that require the least amount of work and deliver the most by using reversible processes. So that means the most efficient cycles are reversible cycles. So if we want to maximize the efficiency, how can we do this? We can maximize Q out. We can minimize, not Q out, work out, or minimize work in, or minimize QH, right? Okay. This is what we want. But we know these 4 components, they depend on how the individual process, depending on their individual process, right? Because this is a steady flow device, boiler, this is a steady flow device, condenser, steady flow device, a pump, another steady flow device, which is a turbine, okay? So turbine has its own process, condenser has its own process, pump has its own process, and boiler has its own process. So as long as we can like optimize the process of every single independent individual device, then together to be a heat engine, then this heat engine can like work in optimum state, okay, which is a reversible cycles, okay. All right. So reversible cycles cannot be achieved in practice, okay? Cannot be achieved in practice. Because of what? Because reversible processes are required to make a heat engine or to make a cycle reversible, but we know that reversible processes do not exist in nature, okay? But even though we still want to use reversible cycles to what? To make some kind of calculations to know their upper limits or lower limits on performance of real cycles. Okay, so that's the purpose, because we want to know the capability of the device we want to design. So we could assume, for example, like if the device, if a heat engine, if I am a designer, I am designing a heat engine, then I assume this heat engine is reversible, and I got the efficiency, for example, like 70%. So 70% is a theoretical limit. And I assume the processes occur inside this heat engine is reversible. Then I got 70% efficiency. Then this efficiency is the maximum, is the optimum. So in reality, these heat engines efficiency should be lower than 70%, because 70% is maximum. And I assume this heat engine runs in reversible processes, but I know that reversible processes do not exist in reality, in nature. Okay, so that we can still estimate maximum performance, maximum work output, things like this. Okay. Okay. So what is this engine? It's actually Carnot engine, or Carnot engine runs in Carnot cycle. Okay. So Carnot cycle, this is, like I said, I believe this is the most important stuff in chapter 6. Okay, Carnot cycle. So it's proposed in 1824, almost 200 years ago, by a French engineer, C.E. Carnot. Okay, and a Carnot cycle includes 4 reversible processes. Okay, remember, 4 reversible processes. So Carnot cycle does not exist in reality. Well, as long as the device involves a reversible process, then this device is like imaginary. Okay, it doesn't exist. Okay, in reality, it just serves a idealization or optimum model for the design. Okay, so 4 reversible processes: 2 isothermal and 2 adiabatic. 2 isothermal reversible processes and 2 adiabatic reversible processes. So all these 4 processes are reversible. Okay. So a Carnot cycle can be executed in a closed or a steady flow system. Okay, it's the most efficient cycle operating between 2 specified temperature limits. Okay. Okay, we will talk about this later, and it's very important. Okay. The idea here is, as long as the two reservoirs are the same, any device operates between these 2 reservoirs. If the device is reversible, then whatever the device is, whatever the purpose of the device, then they would have the same thermal efficiency, as long as they are like reversible. They are reversible devices. Okay, we will talk about this. Well, Carnot cycle involves reversible processes, so Carnot cycle cannot be achieved in reality. Okay. So remember, we have a Carnot cycle has 2 isothermal processes. One is expansion, the other one is compression. And it also has two adiabatic processes. One is expansion, the other one is compression as well. Okay, so you need to keep this in mind. You need to keep the details of the count cycle in mind. Okay, so let's look at the drawing here. So this is a drawing, but the descriptions is here. Okay, process one. Let's look at this first. Okay, process 1 to 2. This is reversible isothermal expansion. It's about expansion. 2 to 3 is adiabatic expansion. So we have two expansions. 3 to 4, this is compression, but it's isothermal compression. Isothermal compression. 4 back to initial state 1, then this is adiabatic compression. So compression. Two expansions, two compressions. Okay. So now let's look at the details. Process 1 to 2 is isothermal expansion. Okay, look at this. The gas is allowed to expand slowly, nicely, which means the system is quasi-equilibrium. Don't forget quasi-equilibrium, this is internally reversible. This is internally reversible, okay. So expansion is the work done on the surroundings, right? Because the piston is pushing the surroundings, doing work onto the surroundings, okay. So the gas is allowed to expand slowly, doing some work onto the surroundings. So the temperature inside the system is supposed to be decreasing, right? However, we attach an energy source, which is high temperature reservoir, onto this device, this system. Okay, so that ensure that the temperature inside the system remains constant and at the same temperature of this high temperature reservoir. Okay. So this heat transfer process, this QH, is in the same temperature. So this heat transfer process is reversible because the temperature of this energy source or high temperature reservoir is the same as the temperature inside the system, right? So this is zero temperature difference heat transfer. So this heat transfer process is reversible. Okay, remember, finite temperature difference heat transfer is irreversible. Okay, but this is zero temperature difference heat transfer, which is reversible. Okay, so as a gas expands, the temperature of the gas tends to decrease, but because there's a reservoir attached to the system, so the reservoir supplies the heat to the gas immediately. And don't forget the definition of the reservoir or energy source. Energy source is high temperature reservoir, so it's a reservoir. So the unique characteristic or the definition of the reservoir is the temperature doesn't change. Okay, so the temperature doesn't change. So even though this reservoir is supplying some energy to the system, so that means the reservoir is actually losing some energy, but because it's a reservoir, so the temperature doesn't change. Okay, so TH remains TH, and the system remains TH as well. So this heat transfer process is reversible. Okay, so the system is expanding, but because there's a heat supplied to the system, so the system's temperature doesn't change. The system's temperature remains constant. Okay. This is process 1 to 2. So this is why it's isothermal. Isothermal means the temperature doesn't change, right? Temperature remains constant. Okay. And it's expansion, so it's doing work on the surroundings. Okay. Process 2 to 3. Okay. So when the expansion is up to this position, then I remove the reservoir and make sure this is adiabatic, which is process 2 to 3. I remove the reservoir and make this side insulation adiabatic, which is adiabatic, right? Then the temperature decreases from TH to TL. This is nature, right? This is nature. When the system is doing work onto the surroundings, temperature tends to decrease. Temperature decreases, okay? Because the system is losing energy because it's doing work onto the surroundings, like you are pushing the air. So you lose some energy. The system loses energy. So temperature drops from TH to TL. Okay. So this is still an expansion process, and because all the sides are adiabatic, so this is adiabatic expansion. Okay. So the gas continues to expand slowly. It's still a cosine equilibrium. Okay. Doing work onto the surroundings until its temperature drops from TH to TL. Okay. Then from state 3 to state 4 is reversible isothermal compression. Okay, so now we are compressing the system. Okay, from state 3 to state 4, this is isothermal compression. So when we compress a system, then the system's energy increases, right? So the temperature is supposed to increase. But in this case, because we attach an energy sink to this system, okay? So the additional energy because of the this compression process is transferred to this energy sink. In that way, the temperature of the system remains constant at TL. Okay, and this energy sink's temperature is also TL. So this QL, this heat transfer process, is reversible because this heat transfer process occurs zero temperature difference, right? Energy sink's temperature, system's temperature, they are the same. So QL is a reversible heat transfer process. Okay. Okay. Yeah, as the gas is compressed, the temperature tends to rise, but because the heat is transferred, this additional heat is transferred to an energy sink immediately. So the temperature of the system remains constant. Okay. Then once again, when we remove the energy sink, there's an energy sink, but we remove it, then make sure this is adiabatic. Then the compression continues so that naturally the temperature increases. Okay. So the gas continues to be compressed in a reversible manner until the temperature returns to its initial state, which means the temperature returns to its initial one, which is TH. So from TL back to TH. Okay. So for reversible processes, You need to keep this in mind, every detail. Okay, reversible. We have two isothermal processes and two adiabatic processes over two expansions and two compressions. Okay, so it's very important. And Carnot cycle is like, yeah, I think it's the most ideal cycle we learn. Okay. Okay. On a PV diagram, if the system, if the working fluid inside the system is an ideal gas, then well, not necessary to be ideal gas, but because we learn ideal gas and we know ideal gas follows ideal gas relation, which is PV equals MRT. Okay, so this is the process curve from stage 1, 2, 3, 4. Okay, so this is the process curve. Okay, and process 1 to 2, there's a QH coming in. So this is a isothermal process. 1 to 2, this is isothermal process. And is an isothermal expansion, right? Because V1, V2, so V2 is larger than V1, so we know it's an expansion process. So it's isothermal expansion process. There's a heat coming in. This heat transfer process is QH. Okay. 2 to 3. 2 to 3 is also an expansion process, right? But this is adiabatic process. Adiabatic expansion, right? Because we remove the energy source and make sure all the signs of the system is adiabatic. So during this process, the temperature decreases because the system is doing work onto the surroundings. Okay, so this is adiabatic expansion. Then 3 back to 4, this is compression, right? And it's isothermal compression. This is isothermal compression process. And because during this process, we attach an energy sink onto the system. So any additional energy coming into the system because of the compression goes to the energy sink immediately. So the temperature inside, the temperature of the system remains constant during this process, during 3 to 4. Okay. Then 4 back to 1, 4 back to 1. This is adiabatic compression. Okay, 4 back to 1. We remove the energy sink and make the system adiabatic again, fully adiabatic again. Okay, so but the compression continues, right? You can see 4 to 1. V4 is still larger than V1. So this is a compression process. When this compression continues, the temperature decreases. The temperature increases, right? This is a compression. So the system is receiving energy because of the compression. And the refraction is the temperature rise. Okay. So this is a PV diagram of a Carnot cycle. Okay. So during the expansion processes from 1 to 2, and then 1 to 2, then 2 to 3, they are expansion processes, right? And this is a PV diagram. So we know that the area underneath the process curves is the work, right? It's the work. So 1 to 2, 2 to 3, this is work out. right? This is expansion process. So this area is worked out. However, from state 3 to 4, then back to 1. 3 to 4, 4 back to 1. This is compression process, right? So this is work input. This is work input. This area represents the work input. So their difference, I will use this. Their difference is the area composed by all these 4 processes. Okay, so this area is a difference between the work input and work output, right? This area. So this area is the net work out, right? You can see the 1 to 2, 2 to 3, this work out is larger than work in, which is from 3 to 4 to 1. Okay, so this yellow area or just this pink area by the textbook, it represents the net work out. Okay, this is a net work out, this pink area. Okay, all right. So remember that in very beginning of this chapter, when we say that, okay, so how about if we make this 0? If we make this 0, then we would have the maximum thermal efficiency, right? But if this is 0, see this, that means we don't have state 4. We would have 4 and 2, they are the same because we want to have QL, right? So during the compression, we won't go back to state 2, then state 2 back to state 1. Okay, so in this case, what would happen? That means there will be no net work output, okay, because the area the area enclosed in 1, 2, 3, 4 back to 1 is 0. Okay, so in this case, 1, 2, 2, 1, 2, 3, 2 to 3. Then because we want to save QL to maximize the efficiency, but in this case, if QL is 0, we want to make this 0. So the compression would go back to state 2, then state 2 go back to state 1. Okay, so there's a line here, 1 to 2. There's another line, 2 to 3. But 3 to 2 is like the same line, it's the same path. 2 back to 1 is the same path as 1 to 2. So the area enclosed in these 4 processes would be 0. Okay, that is what this note states. Okay, like if we want to compress the gas at state 3 adiabatically instead of isothermally in an effort to save QL, we would end up back to state 2, retracting the process path 3 to 2. So by doing that, we would not be able to obtain any network output because the area enclosed in these 4 process curves will be 0. Okay. Okay. This is a Carnot cycle. Okay. Then Carnot principles. We have 2 Carnot principles. This is 1. This is 2. Okay. So let's read this over. So Carnot first principle states that the efficiency of an irreversible heat engine is always less than the efficiency of a reversible engine operating between the same two reservoirs. Okay, so this is like the baseline, the base or the point that, or the common ground we stand by by comparing something, right? We cannot compare like the orange and apple, right? Because they are different fruits. They are fruits, but they are different kinds, okay? So we cannot compare like this, okay? And the Carnot's second principle says that the efficiencies of all reversible heat engines operating between the same two reservoirs are the same. Okay, so graphically, like this. Okay, so we have the same two reservoirs, and we have 3 heat engines. One is irreversible, 2 are irreversible. 2 are reversible. Okay, this one is reversible, this one reversible, reversible. They are heat engines. Okay. By Carnot principle, the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same two reservoirs. So the efficiency of heat engine 2 should be higher than the efficiency of the heat engine 1, because heat engine 1 is irreversible, heat engine 2 is reversible. So reversibles heat engines efficiency is always higher than the irreversible heat engines efficiency, as long as they operate between the same two reservoirs. Okay. Second, the efficiencies of all reversible heat engines operating between the same two reservoirs are the same. So if we have 2 reversible heat engines, engine 2 and engine 3, they are reversible, their efficiency should be the same, as long as they operate between the same two reservoirs. Okay. We can prove this. We can prove this. Let's see this. Okay, so now we have a reversible heat engine and we have a reversible heat engine. These 2 engines operate between the same two reservoirs, high temperature reservoir, low temperature reservoir. Okay, so Carnot first principle tells us that the efficiency of an irreversible heat engine is always smaller, it's always less than the efficiency of a reversible one, right? So now let's make an assumption. Let's say efficiency of a reversible heat engine is larger than the efficiency of this reversible heat engine. Okay. We just assume this guy, this irreversible heat engine's efficiency is higher than this one. Okay. That violates the Carnot principle, right? So we want to prove this is wrong, right? So that means the Carnot first principle is correct. Okay. All right. Then, okay. So now, because this is a reversible heat engine, right? So now we want to reverse the operation of this heat engine. So initially or originally, the heat engine receives heat from high temperature reservoir and converts part of the heat to work output, then dump the raised heat to the low temperature reservoir. Okay, now we reverse this. We reverse the process. So this is what we are looking at. Okay, this process. We want to reverse the process. Literally, we reverse it. Okay, so we have reversible work input, and this is reversible QL. This is reversible QH. Okay, so we don't look at this anymore. We don't look at this. Okay. And one more time, we combine the system. Okay, we combine the system. Okay, but because we assume this irreversible heat engine's efficiency is higher than reversible heat engine's efficiency. So work irreversible, this guy is larger, it's greater than work output. Now it's work input of the reversible engine. Okay, we know this, right? Because we assume irreversible heat engine's efficiency is higher than the efficiency of the reversible heat engine. So we can conclude that the work output of this irreversible heat engine is larger than the work output of the reversible heat engine. Okay. Now, because we are reversing the process of the heat engine, that becomes a refrigerator. Okay, right? So then we choose a new system that includes these two heat engines. Okay, then what do we have? What do we have? Okay, okay. One is, okay, so QH, these two QHs, they are canceled out. Okay, because this is heat received from the high temperature reservoir or heat dumped or heat rejected to the high temperature reservoir. Okay, but in this case, because the work output of the irreversible heat engine is assumed to be larger than the work output of the reversible heat engine, which is now refrigerator. Okay, so QL irreversible should be like smaller than QL reversible. So combine, that's want to so now combine these two processes, right? This guy is QLREV. This guy is QL irreversible. So now we combine these two. Okay. That becomes the difference between QL reversible minus QL irreversible, right? Because of this. Okay. So we have QL going to this combined system. Okay. And this system, you can see about the work output, because we assume this guy is larger than this guy, right? Which is here. So when combining, that means we have a net work output, which is work output of the irreversible heat engine minus the work output of the reversible heat engine. Okay, so we have a net work output. So there's a work output. Okay, But this system violates the Kelvin-Planck statement, right? Because the Kelvin-Planck statement tells us that we need 2 reservoirs in order to have a network output for a cyclic device, right? But when we combine in the system, then there's only 1 reservoir. Okay, we don't need another one. We don't need another one. Okay. And this device, this cyclic device, can still produce network output with only 1 reservoir. So this violates the Kelvin-Planck statement. Okay. So that means the initial assumption we made is wrong. This is wrong. Okay. This is the initial assumption we made. So this is wrong. That means the reversible heat engine's thermal efficiency should be larger than the irreversible heat engine. So we got the Carnot's first principle. The irreversible heat engine's thermal efficiency is always less or smaller than the reversible heat engine's thermal efficiency. Okay, so we prove this. Okay. Then the Carnot's second principle tells us that the efficiencies of all reversible heat engines operating between the same 2 reservoirs are the same. Okay, so we can prove this by a similar method. Okay, we assume they are not the same. So now let's do this. Easier. So we assume efficiency reversible A is larger than reversible heat engine B. Then we can do exactly the same thing. Okay, by like reverse 1 process, 1 heat engine's processes, then combine 2 heat engines to become 1. Then you should be able to prove the same stuff. You should be able to prove this is wrong. This is wrong. Okay. So the correct one is, as long as they are reversible, their thermal efficiency should be the same, as long as they operate under the same 2 reservoirs. Okay. So these two principles, Carnot principles, you need to keep this in mind as well. Okay, it's very important. Okay. All right. So we have just finished the most important part of chapter 6, I believe. Okay. Now let's talk about temperature. But temperature scale, we mentioned, I believe we have mentioned this in chapter 1 when we talk about the temperature. Okay. But here we can look at this. There are some different concepts here. Okay. A temperature scale that is independent of the properties of the substances that are used to measure temperature. Temperature scale, we know we have degree C, degree K, things like this, right? Okay, but see this. The second Carnot principle tells us that the efficiencies of all reversible heat engines operating between the same 2 reservoirs are the same. Okay. Right. We just proved this. So the efficiency of a reversible heat engine is independent of the working fluid, the way the cycle is executed, or the type of reversible engine used. Okay, so that means no matter what that reversible heat engine is, working fluid, process, everything, okay? As long as they operate between the same two reservoirs, their efficiency should be the same, okay? The efficiency of a reversible engine is a function of temperature only, okay? This is the implication of the Carnot's second principle, okay? The efficiency of a reversible engine is a function of temperature only. Okay. It's not a function of the working fluid, it's not a function of the cycle, it's not a function of the process. Okay. So as long as it's reversible, then the efficiency of a reversible engine is function of temperature only. Okay. Keep this in mind. It's also important. Okay, so this is temperature scale. This is in chapter 1. I believe you already know that. Right. So Carnot heat engine. We know the Carnot cycle. Okay, now it's Carnot engine. Of course, is like it's operated based on the Carnot cycle. So it's a hypothetical heat engine that operates on a reversible Carnot cycle. Okay. So thermal efficiency, we know that thermal efficiency of heat engine, of an actual heat engine, should be this. Whatever is reversible or irreversible, based on the definition of thermal efficiency, which is desired output over the required input, we can always get this. We can always get the thermal efficiency is 1 minus QL over QH. But however, for any reversible heat engine, we just learned that the efficiency of a reversible heat engine is a function of temperature only. So the efficiency of a reversible heat engine is function of temperature only. So the efficiency of a reversible heat engine is 1 minus TH over T, TL over TH. Okay, this is so-called Carnot efficiency. Okay, so they look similar. Yes, they do. So all you need to do is just to replace Q with T. Q with T. As long as your engine is reversible, Q replace with T. You can do the same thing for refrigerator and heat pump. Okay, as long as the process, the entire device is reversible, you can replace Q with T. We can prove this. We can prove this, I think later in beginning of the chapter 7. Okay, now just keep this in mind. Keep this in mind. Okay, you can replace Q with T as long as the process is reversible, as your device is reversible. Okay, you can do this. Okay. So Carnot efficiency is the highest efficiency a heat engine operating between two thermal reservoirs at temperatures TH and TL. Oh, one more thing is if you want to use the temperature to get the thermal efficiency, first you need to make sure the process, the entire device is reversible. Second, okay, don't forget the unit. If you use degree C or K to calculate the efficiency using this relation, that would be so different. Okay, so don't forget, use absolute temperature if you don't know what kind of unit you need to use. Okay, because this is someone divided by someone. So using different temperature in different units would have different values, right? Okay. Okay, here. Carnot efficiency is the highest efficiency a heat engine operating between two thermal reservoirs at temperature TH and TL can have. Okay, so all irreversible heat engines, or we know all actual heat engines are irreversible. Okay, so all real engines operating between these temperature limits have lower efficiencies, okay, because we know all actual heat engines are not reversible, okay, and efficiency of actual heat engines should be smaller than the efficiency of Carnot heat engine. Okay, this is what Carnot principle tells us, right? Okay. All right. Yeah. So don't forget, when you are doing this, when you are calculating the Carnot efficiency, the temperature unit you need to use is absolute temperature. Okay. All right. So if this is real efficiency of a real device. So if this real efficiency is smaller than the reversible heat engine's efficiency, then this is a reversible heat engine which does exist. Okay. If this efficiency is the same as a reversible heat engine's efficiency, then your engine is reversible heat engine which does not exist. Okay. Okay. Or even if you have a heat engine and you claim your actual heat engine has a higher thermal efficiency than the reversible one, then your claim should be not true. So it's an impossible heat engine. But I can say your heat engine does not exist at this moment. That's it, right? Because I don't know if you could find any heat engine that has a higher thermal efficiency than a Carnot heat engine. Okay, I don't know. That's the future. Okay. Okay. So Carnot heat engine is most work-producing devices in operation today. Oh, sorry, no, it's different. So most real heat engines in operation today have efficiencies under 40%. Okay, so now we know there's a theoretical limit for a real heat engine, and that depends on the temperature reservoir you operate this heat engine. Okay, right? Because we know even though your heat engine is reversible, then your thermal efficiency depends on temperature only. And these temperatures are the temperature of the high temperature reservoir and the temperature of the low temperature reservoir. Okay. So, okay, 40% sounds pretty low, but now we know when evaluating the performance of actual heat engines, the efficiencies should not be compared to 100% because there's a theoretical limit for the efficiency. For example, for like car engine, car engine is internal combustion engine. So, well, we know the efficiency is 1 if your engine is reversible. This is what we got, right? The efficiency. So usually low temperature reservoir, the temperature or low temperature reservoir for car engine, this is the ambient temperature, right? For a nuclear power plant, sorry. For a nuclear power plant, the low temperature reservoir could be the ocean or the river, right? The temperature of the ocean, the temperature of the river is finite, right? It's usually like, I don't know, 10 or 20 degrees, right? So, but we know at least in a nuclear power plant or coal-fired power plant, TH should be, it's supposed to be much higher than the temperature inside in car engine, right? So as long as the facility is bigger, usually the thermal efficiency is bigger. That's the reason, because in a bigger facility, you could have a very, very high temperature resisting facility, the boiler or something, so that TH is usually higher. Okay. Thermal efficiency of an electric heat engine can be maximized by supplying heat to the heat engine at the highest possible temperature and rejecting heat from the engine at the lowest possible temperature. Okay. So like I said, for car engine, the low temperature reservoir is usually the ambient. But if you want to increase the efficiency of your car engine, you could reject the heat to, I don't know, a bucket of ice. That could work, but the efficiency increment could be just very small. But you need to carry a bucket of ice. That is supposed to have some weight, right? Your fuel consumption will be higher. And by doing that, theoretically, yes, you can increase the thermal efficiency, but if you take other considerations into account, like this, fuel consumption could be increasing because there's you need to carry additional weight. Okay. Or how about this? If you run your car in a tropical area like this, like in Taiwan, and if you run the car in, I don't know, North America, in Canada, in Alaska, then yes, theoretically, the efficiency of their car in Alaska is higher than ours, right? Because their ambient temperature is usually lower than the weather, the temperature in Taiwan. Okay. How about this? Supplying the heat to the engine at the highest possible temperature. So what is the limit for this higher possible temperature? Okay, so we know, again, using the car engine as an example. So we know the car engine is made of usually calcium ions. Then we know if the temperature, even if it's a metal, it's an ion, then we know there's a melting point. So your temperature is limited actually by the material property of the ion, maybe just a few 1,000 degree, I don't know the temperature, the melting point of the iron, or even aluminum or some kind of alloy. Okay, whatever it is, as long as it's metal, then it's supposed to have a melting point. Okay, so there's a limit for this, for actual application. Okay. Okay. Let's try a few examples, very easy. A Carnot heat engine, as shown, receives 500 kJ heat per cycle from a high temperature source, 652 degrees, and rejects heat to a low temperature reservoir at 30 degrees. Determine the thermal efficiency of this Carnot engine and the amount of heat rejected to the sink per cycle. Okay. So the thermal efficiency is 1 minus QL over QH. No matter your device is reversible or irreversible. Okay. But if your device is reversible, which is a Carnot engine, then your thermal efficiency, you can replace Q with T. Okay. If this is reversible, or reversible means this is a Carnot engine. Okay. So in this case, the efficiency is 1 minus TL over TH because TL and TH, they are given. So this is 652 plus 273. Oh, sorry. This should be low temperature reservoir. So this is 30. 52 to 73. Okay. And then we got the thermal efficiency. And we know this is 1 minus QL over QH. QL is 500. Sorry, QH is 500. So we can get QL. Okay. We have thermal efficiency here, and they're the same. So we can get QL. That's it. Okay, easy. Quality of energy. Okay, so in first law of thermodynamics, which is conservation of energy, we know the quantity is conserved. Okay, but in second law, because the how do we say this? Okay, so this is the idea. So we know, okay, so yeah, the quantity is conserved, but quality is not conserved. Actually, quality is always decreasing when we use the energy. Okay, but here the idea is for reversible heat engine, we know the thermal efficiency is 1 minus TL over TH. Okay, so if TL remains constant at 303 K, then if you increase the TH, then the efficiency is higher. Okay, so that means higher temperature has higher thermal efficiency. Then we say that the quality of a higher temperature one is higher. Okay, so our thermal energy has a higher quality at a higher temperature. Okay, so the higher the temperature, the higher the quality. I think, yeah, this statement is based on the thermal efficiency because we like to have like maximize the thermal efficiency, but we know that the thermal efficiency of an ideal heat engine, which is a reversible heat engine, which is a Carnot engine, depends on temperature only. And as long as the temperature is higher, then this reversible heat engine's thermal efficiency is higher. So this is why we say that thermal energy has a higher quality at higher temperature. Okay. So Carnot refrigerator and heat pump. Okay, so like I said, as long as your device, your stuff, no matter it's heat engine, refrigerator, or heat pump, as long as it's reversible, you can always replace Q by T. Q by T. Okay, so this QH becomes TH, this is QL, this becomes TL. Okay, QL, TL, QH, TH. Okay, so the highest COP that a refrigerator or a heat pump operating between the temperature limits can have. This is the COP. Okay, so yeah, this is the same. So the maximum or the best COP refrigerator or a heat pump operating between the same two temperature reservoirs is the highest as long as your device is reversible. Okay, so the conclusion is as long as your process, your device is reversible, then your device is the best. It's the best. I'm saying just best. Okay. Best means if your device is used to deliver work, then your device delivers the most work. If your device consumes power, if your device is reversible, then your device consumes the least power. So least best depends on the purpose of the device. Okay, just like the definition of the efficiency. It's always desired output over the required input, right? For refrigerator and heat pump, they are the same thing. They are the same device, but as long as the purpose is different, then their COP is different, or their performance is different. It's still desired output over the required input. Okay. All right. Look at this COP of a refrigerator. So an inventor claims to have developed a refrigerator that maintains the refrigerated space at 35 degree F while operating in a room where the temperature is 75 degree F that has a COP 13.5. Is this claim reasonable? Okay, so we want to check if this claim is reasonable. All we need to do is, okay, so now let's assume this refrigerator is reversible. So this COP reversible refrigerator, this should be COPR, this one, TH minus TL minus 1, and this is 1. So get this. So TH is 75. This is British unit, so we need to convert it to absolute British unit, so plus 460. Then over 35 plus 460 minus 1. Up here, this is 1. So by doing this, we are just examining that the maximum COP this refrigerator can have is what? It's a number, right? So let me do the math. Minus 1. Okay. So this is the maximum COP this device. If this device is a reversible, then this is the maximum COP. So this guy claims that the actual COP is 13.5, which is higher than the reversible COP. So this is true. Sorry, this is not true. So this claim is false. Okay. Okay. Last one, a heat pump is used to heat a house during the winter. The house is is maintained at 21 degrees. The house is estimated to be losing heat at the rate of this much. When the outside temperature drops to -5, determine the minimum power required to drive this heat pump. Okay, so the key word here is minimum. Minimum power required to drive this heat pump. So this minimum power implies that this heat pump works the best. That means this heat pump is working based on reversible processes, or this heat pump is reversible. Okay, so we know the house temperature maintains constant, so QH dot should be just the same as the heat loss. Okay, so COP, reversible heat pump, this is 1/1 minus what? TL minus TH. Okay, this is the best. This is the best situation this heat pump works, because we assume this heat pump is reversible. Okay, so this is 1/1 minus TL. TL is -5. So -5 plus 273, 21 plus 273. Okay, so this over -1. So this is 11.31. Okay, and don't forget the COP is always this QL over QH, right? No matter what, no matter your heat pump is reversible or irreversible, the COP is always this, right? And now we know this is 11.31. Okay, so we can get QL dot, right? Because we have QH dot, so we can get QL dot. So once you have QL dot, then based on the energy conservation, we know QL dot plus network in should be QH dot, right? This is energy balance. So we can get network input. This is what we want.